So hi there, I'm Alice. Like I said, I've been working to revise and improve the Bevy docs. So we're going to do a quick walkthrough um, of the drafts and do this as a bit of a teaching and learning and editing session all together. So as you can see up on the screen, this is the very first thing that people see. Well, maybe not the first thing, but the first thing they see when they open the book. So welcome to the Bevy engine. A bevy may be a group of birds, but our engine is Rust first. All the safety, tooling, and power that come with a modern systems language. Completely free. It's free of charge, open source, and hackable, with an architecture designed for modularity. Innovative ECS, powered by an ergonomic, full native entity component system architecture that makes writing a clear, performant gameplay and engine logic a joy. Cross-platform. Support Windows, macOS, Linux, web, Android, iOS, and more with a single codebase. Effortless parallelism. A data-oriented design and automatic parallel scheduler provide a high-performance foundation for your game. This book is designed for new and experienced users looking for a thoughtful, explanation-first guide to the engine's essential features. If you just want to try it out hands-on, jump into one of our quick start guides instead. That link is obviously still not there yet. So as the footnotes say, we have limited support for web and Android at the moment. It's not bad, but it's not perfect. It could stand to improve. We don't have any console support yet, mostly because none of us have bothered to go through and sign the NDA and get the kit. And XR compatibility is in development. There's an open PR for that looks super promising.
I'd like to add one thing.
Mm-hmm.
If I understand correctly, Universal Windows Platform, that SDK lets you publish on both Windows and Xbox One. So we technically,
Yeah,
if we have,
with the Xbox Creators Platform, I believe, where it's kind of a kiddie pool, but definitely something that I would like to see somebody try. Um,
yeah, so we technically
Yeah.
have Xbox support.
Nobody's tried, so I'd say that don't bet on it yet.
Yep.
And I vaguely remember hearing that the UWP stuff might change soon, and that there might be more restrictions on that in the near future.
Interesting.
So it might not be
Well,
the best future-facing bet.
We'll have the Steam Deck soon, which is going to be super easy for console-like support. Um, so there's a bit of a stability warning. Bevy aims to be a general-purpose game engine capable of handling arbitrary 2D or 3D games. However, Bevy is still in its infancy, and there are very good reasons not to choose it for your next project. No mature solutions currently exist for animation, networking, or console support. The following are part of the engine itself, but are very immature: audio and user interface. If you've worked with either of those, you're like, okay, yeah, this technically exists, but maybe not fully mature. There's some solid third-party solutions for advanced audio and realistic physics. So that's Bevy Cure Audio for that first link, and Bevy Rapier for the second one, which are both fantastic crates. So while Bevy's modular architecture makes it relatively easy to integrate your own or third-party solutions, be mindful that Bevy does not provide a complete game solution out of the box yet. Contributions to the engine are extremely welcome. But if you want to make something fully featured to make your dream game today, check out Godot instead. Unsurprisingly, Bevy's rapid pace of development means that our APIs will break repeatedly in both deep and pervasive ways. This allows us to refine the engine now, adding new features and fixing problems fast, rather than being tied to a first attempt. That said, updating versions of Bevy is surprisingly painless. We provide migration guides, and Rust's excellent tooling will guide you. Chase the errors until everything compiles again, and you should be basically done. That's been my experience migrating my stuff between the Bevy versions. It's been my experience migrating the engine as we make breaking changes, especially with a good test suite. It's so much less painful to be doing this in a strongly typed language. So we are on to the next page. All right, so we have some setup. How much do you guys really want me to cover the setup page? Maybe this is a better page for you to read on your own. this is going to be really tedious.
Setting up Bevy and Rust in general is like pretty straightforward. So I don't think anyone who's interested in being here for this will need a.
Yeah, and again, this is the sort of thing that is better to have having writing and refer back to as you run into issues. So, in terms of so to get to Ida's question, the cheat book focuses on what I would describe as a cheat sheet, as a cookbook approach, where the philosophy is intended to here's some quick recipes for to say this is exactly what I need to do. I know what I want to do, and I know basically how stuff works. And here's a recipe to say here's how it's done. This is taking a more educational approach and a more higher level approach, and designed to get people comfortable with kind of the foundations and basic components of how Bevy fits together. I've talked with John Madazi a fair bit. I won't put words in their mouth, but it's that's my understanding of sort of the different approaches. And the cheat book is also pretty deliberately unofficial. John Madazi enjoys the little bit of extra freedom there. For Dio, yes, somewhat mature collision detection, use Bevy Rapier. It's quite good. Yeah, I wouldn't really choose to use it for a platformer, 2D platformer, but if you want full 3D realistic physics and colliding bodies and contact forces and stuff, it's a good choice. Yeah, for Jekyll, good. You've got that. All right, so we're gonna move on to apps. So for the apps, Bevy programs store and execute all of their game logic and data within a single app data structure. Let's make a trivial the Hello World app to demonstrate how that works in practice. This process is straightforward. First, we create a new app. Then we add a simple system which creates Hello Bevy when we're done. Then, when we're done configuring the app, we call app.run to actually make our app do things. So, for those of you who are familiar with Bevy already, and are, if you guys spot the typos, please mark them down. So, for those of you guys who are familiar with Bevy 0.5, you'll note that the app builder is gone. You no longer call app build. Everything is now just methods on app, and you call app new. Pretty straightforward, easy migration. But with calling out, so over here, we can see our main function. So Rust always needs a main body within its main.rs for programs to actually be executable. And then we have creating a new app. We're adding a system. We're calling run. And over here, we can see this hello system, which is just a Rust function that we're adding as a system to our scheduler. Yeah, I definitely agree with you, Ida. It's sometimes a little bit hard to split the balance between helping the newcomers and avoiding boring our experienced programmers to death. So over here, we're going to think about what's in our app. If we pull this back, what's actually stored in here? So if we pull up the docs, which I believe should work. No, it's not going to work for you guys. So, anyways, that link brings us to the doc, and in there's three fields. So there's world, schedule, and runner. The world field has all of our game's data, so that's all of your entities, all of your components, all your resources, everything that Bevy can basically see. The schedule holds all of the systems that operate on this data, and the order, the schedule also contains all this metadata about how these systems fit together. And then the final part is the runner, which interprets the schedule to control the broad execution strategy. So are we running it in a loop? Are we waiting for our web request API to ping us? Are we running it a single time because we're using Bevy for extract, transform, load tasks because we feel like it? So you can read more about these by exploring the reference documentation linked just above. If you guys are new to Rust, Rust API docs are so good and so effortless, and you should write your docs in your libraries. Bevy's API docs are actually fairly okay these days. Nillerad has a fantastic open PR for improving all of the docs on the Bevy ECS, and it will make this book much more useful. So, despite all of these primitives of world, schedule, and runner, you're typically not going to be operating on that level. You're going to be operating at a more granular level than these primitives. We're going to be controlling data in terms of the specific resources or components, and we'll be adding systems to an existing schedule, typically just the standard default schedule. To do so, we can customize our app by training methods using the builder pattern. If you guys aren't familiar with the builder pattern, you're basically repeatedly calling configuration tools on a single object, rather than trying to pass in 5,000 parameters all at once. And it works fairly well for this case, and it works particularly well in Rust because we don't have default arguments. So the most basic tools that we get for working with the app are, the first one is we can initialize resources into our world to store global data. Resources basically act like well-behaved singletons. You can only have one of them of each type, and they're accessible everywhere, and but the access is controlled in a way that tries to avoid some of the utter untrackable chaos that you get with true singletons. The next thing that we can do is we can add systems to our schedule that perform logic. And the third basic thing that you're going to be doing a ton, especially within smaller programs, well, I guess larger programs, is you can import other blocks of code that modifies the app using plugins. Or really, you pass in a mutable reference, then it mutates it, but that's nitpicking. So we're going to write a very simple data to demonstrate how all of these things fit together. So here, we start off by importing the Bevy prelude. Where we need all of the standard things, so we just import the prelude as a glob import. Have our main, and we call app new. So plugins are app code that was written elsewhere, imported as a single unit for organization and clarity. So we're adding the minimal plugins at the moment. There's a plugin set, and it basically just runs things through and doesn't crash. It doesn't open up a window. It is not connected to Winit. You could probably run this on a Raspberry Pi and it would work just fine. Resources are global singleton data stored in the world. So here we're inserting a resource of the type message with the field string, which says welcome to Bevy. And these systems run every pass of the game loop and perform logic. So every time the game loop passes, it's going to say welcome to Bevy, and you're going to get spammed to heck in the console when you run this program. Yeah, I agreed. I think that it is in fact missing a .2 string. We are currently setting up a to make sure that all of these examples are compiled, which will help a lot. So here we have a resource. It's just an ordinary Rust struct, and here we're declaring that its field named string stores a string, which is a data type for basically for words in Rust if you're new to programming. Over here, we have a system that reads our message resource, and here we have res message as one of its function parameters, and this automatically tells Bevy to request the data and then extract it in. Oh, and we can remove the .system. Ha, good.
Okay, so I said that I'm new.
Yep.
But I'm not this new. So I'm trying to think if I was like being told by like an employer or something to look into Bevy.
Yep.
Then would it maybe be helpful to add like a clarifying statement to the system that that Bevy automatically converts
Yeah.
functions that take in like
Yeah, so we get
queryable info?
into more details about that later, but that's actually probably worth you writing here as a comment. Could you make a note on the PR?
You got
Awesome, thank you. So, next up, we're going to talk about plugins. So you saw the minimal plugins in the last one. So one of the Bevy's core principles is modularity. In Bevy, all functionality is implemented via plugins, which are added to an app. I'm not sure that framing is totally accurate, but it basically makes sense. The core idea there is that there's nothing special about Bevy's internal logic. There's no, oh yeah, we're using these secret internal only APIs that are too unstable for anybody else to use, but we get to use them to break the rules. No, it's everything within Bevy, like all of the all of our like windowing and rendering and so on, is effectively built out of the same primordial goo that we hand to you to make cool new things out of. So game logic like player movement and core engine logic, like rendering and sound, and third-party extensions like tile maps are all implemented in the same way using these plugins, and you can add and remove them in whatever fashion you want. This empowers Bevy developers to modularly build their own engine using official, third-party, and custom plugins. Bevy intentionally blurs the line between engine developers and app developers, and you see that a lot on this Discord. There's a ton of us who are contributing to Bevy super easy, and you'll tend to find that as you write your own code, you're learning and developing the same skills that you're doing. So the next thing is we're going to go demonstrate how to write our own plugins. So plugins are just collections of code that modify app. Any code in a plugin could be directly substituted onto the base app. There's no magic to be found here. Right now, plugins are just they're just a straightforward tool for code organization. They're not any fancier than maybe slightly fancier than include statements. So plugins are any type that implements the plugin trait. If you're not familiar with traits, basically traits are adjectives that you can give to the different types of Rust, which basically serve as categories. And so some of the common traits that you get are things like copy and debug and so on, which add behavior and define the nature of these types in a way that you can interface with nicely. So here, we're just adding the default plugins as a group, and then we're adding our plugin to the app, a new plugin. So here we're making a score plugin, and then we're calling .run. So in this case, we have a struct score plugin. So this is just a default. This is just a really simple unit struct. This is a new Rust type that we defined, and it doesn't do anything. It doesn't have any data attached to it. But what we can do is we can implement this plugin trait for it. And within traits, they'll often have things called associated methods, which are functions that effectively belong to that new type. And what you have here is we have the associated method build, which takes in itself, and it also takes in a mutable reference to the app. And what it does is you mutate the app, and you say, typically just by method chaining, and you say, we're going to add a resource, and then we're going to add a system, and then we're going to add another system. And in terms of what we're actually doing here, we're making a score struct that's added as a resource to the world, beginning at the default value of 0. Over here, we can see that we derive default, and the default is for the numeric types is 0. The increment score system increments the score by 1 every pass of the game loop, and the report score system prints the current value of the score. Boo! There's so much .system left. Anyways, the So we can take a look at these systems here. We have Increment Score, which takes in a mutable reference to the mutable resource wrapper for the score, and then it actually goes and changes the field value. .0 there means that this is the first value there within that tuple struct, and then the report score takes in a read-only reference in the form of a res to the score, and it reports its value. So next up, we have this idea of plugin groups, and plugin groups are basically just sugar for add plugin, add plugin, add plugin, add plugin, and they are collections of functionality, and the Bevy's default plugins is just a plugin group that adds the core engine features, things that you'd expect to work just right out of the box, rendering, windowing, and sound input handling, and so on, that most developers want when you're building a new game. You can add default plugins to your app using .add plugins, default plugins. It's pretty straightforward. You can take a look at the source if you're really curious. Exactly a list of all the things that are in there. Taking a look at taking a look at the source for Bevy is honestly easier than you might expect. The code base is pretty legible, and again, it looks just like end user code. Everybody else hearing me okay? I noticed Radis said that they were struggling to hear me.
For me, it's totally clear.
Awesome. Sounds good. If you're looking to structure your Bevy app in an unusual way and don't want to use most of the functionality provided by the engine, you can choose to use Bevy's minimal plugins instead. So I've seen people use this for things like for strange things like scientific computing, or I'm using a terminal app, or things like that, and they'll just use minimal plugins instead and build everything else up by hand. And in the source for the straight impl plugin group for minimal plugins, we can see that it adds core plugin and scheduler runner plugin. And what that does is the core plugin just handles the low-level fundamentals, so you're updating the app time and so on, while the scheduler runner plugin sets up the main game loop to run repeatedly over time. The scheduler runner plugin in particular is usually the behavior that you expect from a game engine when you tell it to run. Thank you for reminding me that I talk too fast. I should get better at that, because I absolutely do it, and it's really bad for talking to non-native English speakers. So the next thing that we have is third-party plugins. So importing third-party plugins is easy. They're just ordinary Rust codes that can be managed with cargo. So you just download the crate, and then you tell it to add plugin. So Bevy's modular nature tends to result in simple plug-and-play interoperability and easy extensibility. So don't be afraid to try out plugins that seem interesting or useful for your game. That's one of the things I really like about Bevy is you can find cool new things in the ecosystem, and you can just throw them in your game, and they'll basically work. And then you can hook into all of their systems systems and components with the ECS, and it just extends beautifully. And as a plugin author, you don't need to think too hard about exactly what API you're providing, because it can be extended so comfortably. So the steps to do this: so you find a Bevy plugin, collection of assets. Is solid. BevyEngine.org/assets. The showcase channel here also often has a name. Then we are you add the crate to cargo.toml under the dependencies header, just like you had to do for Bevy, and then you import the code definitions from that crate. So things like using Bevy third-party library, and then imported all of preload to add the appropriate items to your workplace, and then you just add the plugin to your app.add-plugin. If things aren't working, make sure you're following the documentation and examples from the crates you're importing. They often have really useful information there. If you're planning on releasing a plugin yourself, please refer to the Bevy's plugin guidelines. Some folks made up a really nice list of like useful tricks and conventions there. Worth checking out if you're considering it. Then you release a crate, and then you add it to the Bevy assets repo. You just make a pull request to it, and it'll get added in. Pick and choose features. Some apps won't need all of the features provided by default plugins. Other features must be opted into. We can use cargo features to enable and disable what features are compiled into your game. In your cargo.toml file, you can disable features and opt into the features you want. Like so, you add you set default features equals false in your Bevy version, and then you manually select which features you want. So things like audio. This can also be helpful if you're getting stuck and you're for some reason on Linux your audio just isn't working. It's complete shock. You can just disable the audio features, and then everything will compile while you try and actually fix that up. There's also a way to configure which plugins are in the plugin group from within Bevy itself. That example that we link goes over it nicely. So, that is the end of the welcome chapter. Yes, Elsa. So, anybody have any quick questions while I swap branches? Oh. And I'm going to grab... and there is the link to the other plugins. So, now that we are back, we are into the brand new chapter. So there's 2 chapters done so far. There's a great deal. There's a great deal more chapters to write. If anybody is interested in helping write more documentation, either with the book or API docs, I would love to help you. So just ping me over in the documentation channel. So, entities, components, and systems. So here's where we actually start to get into the really interesting, meaty bits of how Bevy works. And that's probably why most of you showed up today, is because you want to learn how to use Bevy, how to think about the new ECS. So, Bevy is fundamentally powered by its ECS, Entity Component System. Almost all data is stored as components on entities, and all the logic is executed by its systems. There's very, very, very few exceptions to this. As we mentioned in the last chapter, all of our data is stored in a world on our app. We can think of our entity component data storage as a giant in-memory database. So, if you haven't worked with databases, you think of an Excel spreadsheet. So each row is an entity representing an object, perhaps a player, tile, UI button in our game. Each column is a type of component, storing the data of a particular type, perhaps the sprite, team, or life of a player entity, in an efficient way that keeps data of the same type tightly packed together. Each cell is a component of a particular entity, which has concrete values that we can look up and change. We access data from this database using queries, which fetch entities with a specified component. And the primary key to this database, so the column that you would find all the way over on the left, or the row number if you're used to Excel, is the entity identifier, which is basically just a U64, and can be used to look up specific entities using query's get method. Of course, this database is very ragged. So for those of you who aren't familiar with ragged databases, basically just means that not all of the cells are filled. Some rows will be missing some columns, or vice versa, depending on your perspective. Not all entities will have every component. We can use this fact to specialize behavior between entities. Systems only perform work on entities with the correct combination of components. You don't want to apply gravity to entities without a position in your world, and you're only interested in using the UI layout algorithm to control the layout of UI entities. When we want to go beyond this tabular data storage, we can use resources. Global singletons which store data in monolithic blobs. You might use resources to interface with other libraries, store unique bits of state like the game's score, or store secondary data structures like indexes to augment your use of entity component data. In order to manipulate and act on this data, we must use systems. Systems are REST functions that request specific data, such as REST and entities, from the world. They define a query in their parameters that selects data with a particular combination of components. All of the rules and behaviors of our game are governed by systems. Once systems are added to our app, the runner takes in this information and automatically runs our systems, typically once during each pass of the game loop, according to the rules defined in their schedule. Bevy's default execution strategy runs systems in parallel by default, without the need for any manual setup. Because the function signature of each of our systems fully defines the data it can access, we can ensure that only one system can change a piece of data at once, although any number can read from a piece of data at the same time. That's the core of how Bevy's parallelism work, and it's the same rules that Rust's ownership model and no mutable aliasing, no aliased mutability, that's the word, works, and we can only do this because Rust is so lovely with all of its ownership and memory safety. Systems within the same stage are allowed to run in parallel with each other as long as their data access does not conflict, and are assigned to a new free thread as soon as one is free. That's why we read it over. When we need to access data in complex, cross-cutting ways that are not cleanly modeled by our system's function signatures, we can defer the work until we have exclusive access to the entire world's data, executing commands generated in earlier systems at the end of each stage, or performing complex logic, like saving the entire game in our own exclusive systems. You will first encounter this when spawning and despawning entities. We have no way of knowing precisely which other components our entities might have, so we are forced to wait until we can ensure that we can safely write to all component data at once. So here we're going to get into our first actual real example, so ECS by example. So before we dive into the details of each of these features, let's take a quick look at a simple game that you can run and play. Game is a bit of a stretch here, especially now that we've changed the example, but game like a program. Unsurprisingly, the different parts of the ECS tend to be closely linked. Components are not very useful without a way to spawn entities, and systems that run our logic are very dull if we can't discuss the data that they can access. The details of each part are more easily grasped if you have a basic sense of the whole. So let's get started. So first off, we're importing at the top of our function, like all Rust functions, all Rust files tend to do, all of the things that we need. So we have the prelude here, which is the standard, all of the normal things that we want. We're also importing a log plugin and app exit, so we can quit the game. So over here we have our very first component with derive component. If you're new to, if you haven't been following the dev chatter, components are now require an explicit derive, because this will help us avoid stupid bugs and enable cool new features. Mostly in terms of bugs, it will prevent us from mistaking components and bundles when you're inserting them, because this leads to horrible things that are awful to debug, especially for beginners. So our first component, it just defines our entity's life total. It just has a float 32 inside of it. And then we have a second component to mark whether a entity is currently airborne, and if it has that, it has a height component, which is the initial height of falling. This example is from Nilirad. Thank you so much to Nilirad. So the higher that you fell from, the higher damage that you're going to take. But we'll get to that logic in a second. So next up, we have our main function, which contains all of our app logic, and so we're creating a basic framework using the minimal plugins again. Log plugin is we're grabbing one of the default Bevy plugins and adding it, so then we can use the info macro to actually report things to the terminal. Less blocking than print line, so it's probably better practice. And then over here, we have a spawn player system. So because we've added this system as a startup system, it runs exactly once before any ordinary system. That's how startup systems work. They're super useful for things like spawning in entities. Next up, we have ordinary systems. We have a gravity system that runs once per frame or past the game loop. In this case, we don't have a frame, so we're just running it as fast as we can. And we have a gravity system, and we're labeling it gravity. And then over here, we use this label and to make sure that you report the fall damage after gravity has applied. Systems within Bevy run in a non-deterministic order unless you tell them not to. This helps them run faster when you don't care, and avoids brittleness where you have implicit ordering and then you go and change something in your app that you didn't think should matter at all, and it breaks all of your assumptions about how things should work. So next up, we have a system. It's going to spawn a player. They're going to drop from the sky. We have a constant for their initial height. And that initial height is 15. So entities can be spawned in delayed fashion with commands. So here we have commands, which was requested as a system parameter using our functions. And we have commands.spawn. So this creates a new entity. Then we're adding components to the entity by calling .insert, and we're .inserting life, giving them a life total. Then we're giving them a transform. Transform is the standard position coordinate component. And here we're just using one of the helper methods to spawn them in at 0, 0. And then we're adding the falling component with the initial height. So the next thing that we're going to do is we're going to spawn a second entity. So this will effectively be a second row of your database, and they will have the same two columns. They're going to actually, this one has, the first one had values in both life and falling because it has the life and falling components. This one and transform. This one just has life and transform. So, like the comments say, we can change its entities are effectively dynamically typed. You can add and remove arbitrary combinations of components, and by doing so, you can customize the behavior that they're going to do. And as a result, when we actually go and apply the gravity system, only the entity with the falling component is actually going to fall. So here, this system pulls the entity towards the ground at y equals 0 at a constant velocity, which is entirely physically realistic, I swear, and it only occurs while it's falling. And the with falling filter, so over here we have a query, and this is called a query filter, ensures that only entities with the falling component are affected. So here we have a gravity system. We define a constant because you should use constants. Please try not to use magic numbers in your code. They're hard to follow. Define a constant, use the constant. So here we are performing the same operation on each entity returned by the query using a for loop. This is super common. You will see this for x in query.iter, you will see that idiom constantly. It's very, very useful and works straightforward. If you prefer the functional style of .for each or .map, you're welcome to do that too. It works just fine. So here we are changing our transforms. So transform.translation means grab the transform and then grab the translation of each field of that transform for each entity, and then grab that field of the translation field called y, and then we're going to set it to the previous translation minus the fall rate with a max of 0, because we don't want people to fall to the ground. Yeah, I am definitely... Yeah, there's kind of a trade-off between how much do you want to encourage optimal code quality versus realism versus simplicity. So in this case, the example is should you be using delta time for this? And the answer is probably yes. The question is it worth complexifying it? And I think that actually in this case it is, because this shows how resources are used. So that's actually a good call. I think that's probably worth calling out. If somebody could add an issue, add a comment on the PR, that would be much appreciated so we don't forget. So here we have a very simple falling damage system. So here we have the system deals damage to falling entities based on the height, and we're grabbing the commands again because we're going to need to remove a component, and we have. So here, this is a nice little trick. It took me far too long to get to understand. Here we're querying for multiple components at once, wrapped within a tuple. And those will be returned in order. But the critical thing there is that entity is not actually a component. It's a piece of data that's associated with each entity, so we can query for it as well. And what it does is it serves as the primary identifier, and it works fantastic. So this will give us the primary key that we can then use for other things. And then here we have an event writer. Event writers are really nice sugars for working with event resources. And we have it for app exit because we want to exit the game when we're done, because we don't have anything left to do once it's done. So each of the components in our query must be present for an entity to be returned in our query. So this system here, this loop will pass over the first entity that we spawned, but not the second. So this line here, info damage, will only show one instance of damage. Then we have so here's the logic here. So here we are unpacking each of the elements of our query into the individual components. So we have the entity type, we have the life, we have the falling, we have the and we have the transform. Note that we need to tell it mute wherever we want to be able to be changing it. So if they've touched the ground, set their position to exactly 0, so they don't over-penetrate the ground too bad. And we're using entity information from our query to ensure that we're removing the falling component from the correct entity. So this is commands.entity remove falling. So this is a type parameter that we're passing in. So because we need to refer to which type of data are we going to be removing, and over here we're using this primary key that we grabbed from the query to make sure that we're applying the .remove command to the correct entity. And the other logic, so here we have our damage calculation logic, and if the falling damage is small, so less than 3, it doesn't hurt the player at all. And the next thing, and then we are saying that the life, we subtract the damage from the life, but again, making sure we don't go below 0, and then we say, then we report how much damage was dealt. Finally, once we're done, we're going to exit the game as soon as the first entity collided with the ground. So, as a bit of an explanation in terms of delta time and why you want to use delta time, games will often jitter in frame rate, and you don't want that to badly affect the movement speed. You see that in very early DOS games where if you play Space Invaders on a modern PC, everything will be moving 5 times as fast as it should be. Don't do that. You want it to actually be relative to the real time, and using delta time and scaling everything according to the frame rate helps compensate for that.
So, Alice, is it possible to have systems update at different frequencies and potentially not update on every frame?
Yep. So that's what run criteria are for, and in particular, fixed time step run criteria is designed precisely for this. There's some debate whether you ever want more than one fixed time step. Talk to Joy about it in the server if you want to get into it. But yeah, fixed time step run criteria is how you control that at the moment. So, next up, we are into our first page of the ECS chapter. So, entities have components. As we discussed in the introduction to this chapter, entities represent objects in your game world, whose data is stored in the form of strongly typed components. Spawning and despawning entities. Before you can do much of anything in Bevy, you'll need to spawn your first entity, adding it to the app's world. Once entities exist, they can likewise be despawned, deleting all of their data stored in the components and removing it from the world. There are 2 APIs to do so. The first is more direct, allowing you to add and remove entities directly on the world. This is going to be this API is going to be much more useful if you're working with Bevy ECS directly. Usually, when you're writing standard Bevy games, you're never going to touch spawning entities like this, except in tests. So here we're creating a world with a world colon new standard constructor, creating a new world, and then we are telling the world to immediately spawn it, and it works immediately because we own the world. Nobody else can mess with it while we're busy mutating it. Next up, we are spawning a second entity, and we are storing its entity identifier in my entity. So my entity there is of type entity with a capital E. Then we grab this. We use this unique identifier that we stored to then go and despawn the second entity. So the second approach is very similar. It uses commands. It works exactly the same as the previous example. And here we are spawning it, then spawning a second one, grabbing its ID, and then despawning the second one. The basic idea with commands is each system that requests commands gets a copy of commands, and then you append on instructions to be executed at the end of the stage. Did you have a question? All right, I'm gonna move on. So you can read all about the details of commands later in this chapter. There's another escaped parentheses. So, working with components. Entities are entirely bare when they're spawned. They contain no data other than their unique entity identifier. This, of course, is not very useful. So let's discuss how we can add and remove components to them, which store data and enable behavior through systems. Defining components. To define a component type, we simply implement the component trait on a Rust type of our choice. You will almost always want to use the derived component macro to do this for you, which quickly and reliably generates the correct code for this trait. Any underlying component data must be send plus sync plus static, enforced by the trait bounds on the component trait. This ensures that the data can be sent across the thread safely and allows our type reflection tools to work correctly. So, with that theory out of the way, let's go and define some components. Yeah, I agree with you. I'm somewhat in agreement with you, Ida. It's direct world access there. I think feels out of place on a read, and the Bevy ECS users I think are advanced enough and can go and read the Bevy ECS interface there, and then we can talk about it. Talk about the other stuff later. Could somebody please add a comment to that section on the pull request, so then we can go and fix that up. And that again, it's nice to cut stuff that is confusing or distracting, because then the very introductory material can be a lot more straightforward. So here we are deriving a component for a struct called component. As you can see, combatant rather. It doesn't have any data of itself. It's called a unit struct in Rust. In Bevy, you actually end up using unit structs a ton. They're useful for distinguishing similar entities or toggling behavior off and on, and colloquially we refer to them as marker components. So if you hear somebody talk about, oh yeah, just add a marker to that, or this is a marker component for the chilled condition, that's what they're referring to. You could have dataful marker components, but the idea is quite similar. So here we have some simple components that wrap a U8 in a tuple struct. So we have life, attack, and defense. That's interesting that you've never heard it. I've heard chatter about it in the server. Yeah, marker. Yes. I apologize. My R's are not always the crispest. And then next up, we have a tuple struct that stores our two ordered pieces of data, just two I32s. And then, in general, I would urge you to please use name struct over tuple structs for anything that isn't completely trivial. Because if you have field names, it's much easier to avoid stupid mistakes and communicate your intent very clearly. So here's the syntax for how named structs or just structs are defined in Rust. And here we have some stats with strength, dexterity, and intelligence. And finally, you can, well, second, almost last, you can actually use enums as components just fine. And enums are incredibly powerful in Rust. You should use them everywhere you possibly can, pretty much, and they work fantastically as components. You just stick them in, and you can then go and toggle their behavior correctly. Here we have allegiance, friendly, neutral, or hostile. It's a realistic example of what you might actually want to use a enum component for. So the last bit is we can store arbitrary data in a component so long as it has a static lifetime. Types without lifetimes are always static lifetimes, allowing us to safely hold a string, but not a ref str. I have no idea how to actually pronounce that in writing. And here we're just driving the name and storing a string in it. So yeah, don't try it. If you're storing text data in your components, store strings. Now we're going to spawn some entities with components, and we're going to use entity commands insert to do so. Yeah, I agree with you, Meatball. So for context, Glam has a IVEC2 field that would be a more natural fit for the sort of position data, because it's already had a lot of useful primitives defined on it. It's not very useful here as a teaching example, because we want to demonstrate a little bit more about how you can store multiple different fields on tuple structs, mostly as an introduction to how to write tuple structs for people who are new to Rust. We got a surprising number of folks who are new to programming or new to Rust in here. Yep. So here we are spawning some combatants. So we spawn an entity, and then we call .insert as part of that chain. Inserts a dataless combatant component into the entity we're spawning. We can configure starting component values by passing in concrete instances of our type. So in this case, we're passing in 10 to the life. By training .insert method calls like this, we can continue to add more components to our entities. And we're going to continue to add attack, defense, position, and so on. Instances of named structs. So instances are actual the actual things that we actual concrete examples of things that we want to do, and then enum instances are created by picking one of their variants. And then finally, we're inserting with this first entity. We're going to call him Gallant. So in terms of when do we want to split and when do we want to not split components data. So in this case, the question is, should stats be 3 separate components? 3 separate components is strength, dexterity, and intelligence. The answer is maybe. It really depends on how you use them. If you're going to be repeatedly using all of the data together, or you want to have a common API, I tend to like merging them into a single component. So in this case, like, if we're extrapolating this wildly, having a stat bundle, a single stat component, and then being able to pass in that single stat component when you're going to make ability checks, for example, or like is going to be less cumbersome than passing in separate components every time. And it also allows you to go and change the internal details without then having to go and update it everywhere else within your code. So there's kind of a yes or there's kind of a trade-off to be made there, and it will really depend. But in general, smaller components are going to be nicer to work with. The other so in terms of merging the repeated insert calls into the tuple bundle, this is in fact nicer. This is why shortly below we go and use this to explain how bundles work. This is a nice teaching technique where you go and show people how much the simple way kind of sucks to motivate the use of a new tool. So we've ended our command method chain using a semicolon. Semicolon is Rust's way of knowing that a statement is finished. So now we can create a second entity by calling .spawn again. So we do the same thing. We spawn it in with some different stat values, and this is an enemy combatant whose name is Goofus. Of course, it's Goofus and Gallant. So for those of you who are not familiar with the obscure like 1920s pop culture reference, Goofus and Gallant is a comic strip about two young boys. Goofus is a troublemaker, and Gallant is a role model, and it's that's where those names come from. So here we're adding and removing components. So once an entity is spawned, you can use commands to add and remove components from them dynamically. So here we have an in-combat component that we're going to be adding and removing dynamically. This query returns the entity identifier of all entities that have the combatant component, but do not yet have the in-combat component. So here, in our start combat system, we're grabbing the entity identifier of everybody with combatant component and without in-combat. Okay, and wow, I'm missing a bracket there. Compilers are powerful. And the next, and then we also grab commands as our second system argument. And then for each of the entities in a query that we're iterating over, we are inserting the in-combat component. And then, end combat system, which does the opposite, and it grabs everybody with the combatant component and with the in combat component, and we are going to just remove them at the end of the current stage, using the same sort of logic, using the entity as the primary key by which to look things up again. This is a common pattern. Don't be afraid to if you need to refer to another entity, just store its entity identifier and then look it up using query.get or similar tools. So, bundles. As you might guess, the one-at-a-time component insertion syntax can be both tedious and error-prone as your project grows. To get around this, Bevy abstracts these patterns using bundles, named and typed collections of components. These are implemented by adding the bundle trait to a struct, turning each of its fields into a distinct component on your entity when they are inserted. So, as you can see here, this is the short code, except it's supposed to have another curly brace to the left. So we're going to try rewriting that code from above using a bundle. Here we have life, attack, and defense, which are... that's bad. That's an actual error. If somebody could note that, that would be fantastic. So here we have... Oh, and I'm missing a comma. Here we have our Combatant Bundle, which is a... which has a collection of components. Each of those names on the left in lowercase are used to assign a field value to of this type. Each of those types that we have is going to be reflected in the final entity that we're inserting the bundle into as a new component. Bundles are basically just convenience methods. They don't exist at runtime. And here we are, as we can add... Of course I'm compiling code as I go. It's much simpler that way. We can add new methods to our bundle type that return self to create principled APIs for entity creation. Self is just a shorthand for whatever this type that we're implementing the trait for. So this return type could be Combatant Bundle. The default trait is the standard tool for creating new struct instances without configuration. So here we are implementing the default trait, and we are setting some default values for each of these stats within it. So has allegiance neutral, 10 strength, 10 dexterity, 10 intelligence, and so on. So the next thing that we have is we have another spawning system, which would be a natural startup system again. And here we are using this what's called struct update syntax to modify the instance of Combatant Bundle returned by its default value. So what this does with this .default method is we start with a Combatant Bundle of value of the value returned by this default ::default, and then we are changing some but not all of the fields. We are overriding them, and then everything else will stay the same as before. And this gives us the exact same. The final entities created by both this system and the same system example above are the same. And note that instead of a .insert, we're using .insert bundle. That's the only difference. It works pretty much the same. And you can continue to chain on insert or insert bundles after it to just keep on adding more components and extending the behavior. Instead of .spawn .insert bundle, you can use .spawn bundle. It's just sugar. There's nothing special happening there. Finally, we have nested bundles, which are a somewhat more advanced tool. You probably won't need them if you're just starting with Bevy. As your game grows further in complexity, you may find you want to reuse various bundles across entities that share some but not all behavior. One of the tools that you can use to do so is nested bundles, embedding one bundle of components within another. Be mindful, this can lead to overwrought, deeply nested code if overused, and bundles are not currently checked for duplicate component types. Adding more components of the same type will overwrite earlier ones, including if they're stored within the same bundle. So there are some caveats, but let's take a look at the syntax. And in this example, we're converting the bundle above to a nested one. So over here, we are creating a new bundle. It's an attackable bundle that stores the life, attack, and defense of our entity. Here, we have, here's where the magic happens. This attribute macro marks our attackable bundle field as a bundle, allowing Bevy to properly flatten it out when building the final entity. In terms of, is there a way to make the Bevy's bundle derive macro detect duplicate components to give the compiler error? Maybe, probably not right now. We wish. That link, they're not currently checked. I'll paste it to you, because that currently is our issue for that is not, the duplicate bundles are not checked. And it's unfortunate. It's macros, Radis. This is how they are checked at runtime, and they'll panic. But the compiler would be good. So now we start getting into a little bit more interesting stuff. So here we have queries, fetching data with queries. Once we have data stored on our entities in the form of components, we need to be able to get that data back out in a principled way. Queries are precisely that tool, allowing us to carefully request sets of entities from the world that meet the criteria we care about, and then retrieve the data we need to operate on. If you're familiar with databases with things like SQL, the fundamental precepts are the same. The main difference is that at the moment, Bevy does not have a way to look up components by value, because that doesn't play very nice with our ECS architecture. Once we have indexes, I am hoping that we can extend this to have some tools to quickly filter components by value. But with that digression out of the way, the query is your primary access into the data in your Bevy game, allowing you to carefully access exactly the data you need from the entity component data storage. The query data type has two type parameters. So type parameters are stored in those angle brackets. The first describes which data should be requested, and the second optional type parameter describes how it should be filtered. We can request access to a single component, life in this case, by adding the query ref life to our system parameters. This will request a reference to the life component on every entity that has that component. This reference is read-only. We cannot mutate the values contained within. If we want to be able to change these values, we need to use query ref mute life instead. And remember to set our query function parameter should be mutable as well. So we can see these examples with read life and write life just below. In order to access multiple components at once, we need to replace our single ref life component with a tuple type that bundles many types into one. Concretely, query ref life, comma, ref attack, wrapped in parentheses, gives us read access to the life and attack components of all entities who have both of those components. Be mindful of this factor when designing queries. Queries operate using AND logic, unless you use an option query parameter. Adding more components will always strictly reduce the number of entities returned by your query. We can get mutable access to the life and attack component separately by changing our ampersand reference to ampersand mutable reference on the components that we want mutable access to. And again, it's Cargo, Rust C will warn you about this, Clippy will warn you about this. Don't request mutable access that you're not going to use, because it blocks your scheduler and is bad hygiene. So, iterating over queries. Once we have a query, the most common thing we're going to want to do is to perform some logic on every entity returned. To do so, we can use straightforward for loops. So here, we have some components, life, incoming damage, and what we're doing is we have a system that report life, and all it does is it prints the current life, a total of every entity with the life component. And and here we have a query parameter, query ref life. So this is read-only access. And for life in query.iter, we're going to debug the life value. We're just going to print it out. Then over here, we have another component called age, and we're going to increment the age. And we have so here the examples is we have because it's mute, we need a mute here in front of query where it doesn't exist. Thanks compiler. Then we need a ref mute, and we need a mute age, and we need a iter mute. So you need to make sure Rust is very picky about the distinction between mutable and immutable reference. You need to follow the compiler. It'll tell you tried to use this mutably, but it wasn't declared as mutable, and then you should go and add the .mute anywhere where it tells you to. Here we have age.0 equals age.0 plus 1. And this is a age.0 is just the first and only field of our tuple type. Again, why I sometimes recommend we're using named structs, because then you don't have the .zeros everywhere that are hard to read. The other tool that you can use is you can implement base types like add to it, and or add a sign. You can implement those traits on arbitrary structs that you have. That can generally make it a lot more ergonomic. If you're familiar with Python, these are morally similar to magic methods, but much more flexible. Finally, we have a take damage system that we're demonstrating, and we're demonstrating how you can unpack your iterator into several variables that you can use in your loop. So here, this is destructuring syntax, I believe it's called, and we are using and here we have we're destructuring this query into the life and the incoming damage components, so then we can modify both of them. And note that this is in order. I strongly recommend using Rust Analyzer or another IDE extension so you can automatically see the types of these so you don't get tripped up. For those more experienced with Rust, you will be unsurprised to discover that you can also use iterator constructs like .foreach, .map, and .filter to work with your queries. They work pretty much just fine. If you find yourself needing to iterate over all pairs or triples or so on of a query, perhaps for collision detection, turn to the Bevy ECS, turn to the iter combinations method demonstrated in the corresponding example to avoid biochecker headaches. That was a wonderful addition by Frizzy for 0.6, and it's been quite useful in case you need it. So Meatball's suggestion is controversial. You are welcome to make a PR that proposes that, Meatball. I'm not touching it. The derive more crate is probably actually worth mentioning, though. Can you please leave a comment to that effect? So, next up, we're going to talk about a special syntax for queries that return only one entity. When we have a query that we know will always return a single entity, iterating over the query tends to result in unclear code. To get around this, we can use query single and query single mute methods, depending on whether or not we need to mutate the return data. Note that these functions return a result. If you expect that this code could fail in real scenarios, in case the query does not contain exactly one entity, handle the return values properly. Otherwise, you can just call unwrap on it to make use of the data quickly. The next thing we could do to talk about is looking up at specific entities using that primary key pattern that I was talking about. So each entity in our ECS data storage has a unique identifier given by its entity, which defines the entity in terms of a U32 ID and a generation. we can fetch the entity of each the entity of each entity returned via our queries by including it as part of the first type parameter of query, as if it were a component. Although no ampersand is used. That's a common beginner mistake. So here we have this system, which reports the entity of every entity in your world. This is actually like fairly useful for debugging, to just get a list of all of the entities and to just spit them out. So we're querying for entity, and every entity in your world will have this. Will match this query, and so everything will be in there. And then debug will just spit out the debug information right into your console. Typically, you'll want to combine this pattern with query filters to extract the entities of a relevant subset and store it somewhere else you can access later. So this system, called Identify Yourself, says we're querying for the entity that has this marker. And then we have a resmute. We have a resource of my entities, which stores a vector of entities. And then for every entity that we get in this query, so all of the entities that have the marker component, we are adding them to that vector by pushing them onto the end. Once we have a particular entity in mind, we can grab its data using the query get method and the related and its friends. This is fallible, so it returns a result that you must unwrap or handle, as you might expect. So the next nice trick to know with queries is optional components in queries. If we want a query to include a component's data, if it exists, we can use the option query parameter and the first type parameter of a query. This can be a powerful tool for branching logic. Use match on the option returned, particularly combined with marker components. So this basically gives you a way to perform OR logic on your queries, where you say, okay, I want everything that's a fruit or a vegetable, and rather than having to construct two separate queries and then join them manually and compare them, you can just request option fruit, option vegetable, and then you'll get some fruit if that component exists. Query filtering. When components are fetched in queries, the data of every component in the first type argument passed will be fetched and made available to the system. However, that isn't always what you want. In many cases, you just want to filter the query based on the presence or absence of a component and don't want to deal with unpacking data you're never going to use. This is particularly true when working with marker components because they don't have any data that you care about. Fortunately, query has two type parameters. The first describes what data to fetch, while the second describes how the entities would be returned by how the entities that would be returned by the first type parameters are then filtered down. So the model here is that query filters only restrict the entities that are included; they never expand it. The two most important query filters types are with and without, which are filtered based on whether or not an entity has a component of the type in the generic type argument. So let's demonstrate by filtering some fruit. So here we have an enum of fruits. This is an exhaustive enum. This is all of the fruits that exist in our world. There's only apples, oranges, durians, and kiwis. And we have a couple of little marker components for whether they're delicious or rotten. Here we are storing how many of each fruit we have using a hash map resource. And what we have a little system to take inventory of the fruit that we have, and this has our little query, and it says we're going to query for all of the fruit, and we're going to take the resource. And as you can see, the second type parameter just isn't there. It's completely omitted. That's nice by Rust to make sure that we don't have to constantly write garbage for the defaults. And so here we are demonstrating some simple some simple hash map logic where we're increasing the number of food that we have in our hash map of that type each time that we discover a food. So here we are talking about with queries. With restrict your queries to only those entities who have components that match all of the data requested and all of the with filters. So here we have a clean inventory system where we're looking for all of the entities that are rotten, and then for every entity that has that was returned in our search for rotten food, we're going to despawn it because we don't want rotten food in our store. And finally, you can combine query filters by passing them in as a tuple, and this will return all of the entities that meet all of the query filter criteria. So in this case, we have an eat fruit system, and we're querying for some fruit, and we're asking it to include only those entities with the fruit component that are not rotten and are delicious by virtue of which components they have. Yeah, I agree. There's definitely there definitely needs to be some code quality review on that system. So you probably noticed that a query for fruit and delicious always returns the same set of entities as a query for fruit with delicious. So what's the difference? So by using with filters instead of requesting the data directly, we only check that a component has that value rather than fetching that component's value. This is nice because then you don't need to unpack our query into a two tuple that we never use the second element. And as a bonus, you can allow other systems can change the value of your components that are only included via with filters. So the next up is OR queries, or query filtering, really. So by default, query filters, just like query data requests, operate on an AND basis. If you have a filter for with A and another filter for with B, only entities with both A and B will be fetched. You can change this behavior by using the OR type, and you nest primitive queries like with and without and changed altogether inside of it to return entities that meet any of the criteria inside. So if we wanted to purchase fruit that was delicious or cheap, we would use something like or with delicious with cheap as the type of our query, allowing us to change the owner of any delicious and cheap fruit that we found. Note that the OR type and other query tuples can be nested indefinitely, allowing you to construct arbitrarily complex logic. So the next bit is a little bit more advanced. So if you you may have run into this and just thrown up your hands as to what the heck has gone wrong. So as the logic in your systems becomes more complex, you may find that you want to access data from two different queries at once. In most cases, simply adding a second query as another second system parameter works perfectly fine. So here we have a defense OR system, which has an OR query and a target query, excuse me. In this case, we are querying for a transform and a creature with an aura, and then we're asking for the transform and defense of everybody else that's nearby. And this just works. But as you go and extend, as you go and play with more things, you may encounter some horrible error that says this query in this system accesses a component in a way that it conflicts with a previous system parameter. Allowing this would break Rust's mutability rules. Consider using without T to create disjoint queries or merging conflicting queries into a query set. So we're going to discuss how to actually do that thing that the error message helpfully tells you should do. So what went wrong? It worked just fine before. So It turns out that Rust, in its infinite wisdom, does not like it when you access the same data in multiple places at once, if at least one of those accesses is immutable. Mutable means that you can change it. That's a result of its ownership rules. We can mutate data in the first query, while the second query is trying to read the data, resulting in undefined behavior, which now undefined behavior is bad. You shouldn't have undefined behavior. We're not writing C. It's just bad. So Bevy doesn't let you do it. And so, but you think to yourself, no, Russ, you're being silly. I've designed my system, and here we have our player query, and here we have our camera query, and you know for a fact that you're never going to do something so stupid as to have an entity that has both the player and the camera component on it, right? And so you're never going to be accessing the same transform component twice. Unfortunately, Rust doesn't know that. We can fix this by making sure our queries are disjoint, no matter what bizarre entities might exist, through the judicious application of without queries. So here we can see how we can force these queries to be disjoint by adding without player there, because the first query, the player query, has with player. The second query has without player. There's never going to be an entity that belongs to both with and without the same component. This is set theory. So the basic idea is the basic idea here is by using without, you can force the queries to be disjoint in order to satisfy the borrow checker. So the other approach to do this is to use a query set. And what this does is it permits multiple conflicting queries to exist in a single system. And these are genuinely conflicting. There's no, oh yeah, well, they're actually disjoint. They can actually access the same entity's data mutably at once. The catch is that you can only access one of the queries at a time. And query sets can be useful when you need to access genuinely conflicting data. Such as if you actually had a bizarre entity that actually had player and camera on it. And you may actually want to do that if you had two loops of your system and then actually did that. So to do that, you can use a query set. That query set logic is going to be outdated, but the compiler will catch that. Kurt has modified it. And so in general, I would recommend that you use disjoint queries first, and query sets kind of as a fallback. They're not as flexible, they don't tend to make as much sense, but there are sometimes real cases where you need to use them, where you want where you want invalid accesses within the system in a way that the compiler can't penetrate. So Bevy systems automatically run in parallel by default, so as long as the scheduler can guarantee that the same data is never accessed in another place while it is being mutated. As a result, we can use the same query filtering techniques described to allow our systems to safely run in parallel. In addition to improving parallelism, so I think this section can be cut. Can somebody please make a note? This doesn't belong here, and it belongs in the system ordering section that will be in the next chapter to be written. So, resources. Resources are global singletons. Not all data is stored in the entity component data storage. Resources are the blanket term for data that lives outside of entities and their components, but are still accessible by Bevy apps. Each resource has a unique type. You can only have one resource of each type, and can be accessed in systems by adding either res for immutable read-only access, or resmute for mutable read-write access as a system parameter. In effect, resources serve as well-behaved global singletons. They're accessible by any system in the app, and because you can only have one resource of each type, are unique. You might want to use resources for things like storing events, holding configuration data, storing simple global game state that you only need a single copy of, like a game's score. Apologies about that typo. Interoperating with other libraries, providing faster or supplementary lookup data structures for entities such as indexes or graphs, and storing reference counted handles to assets so they're not unloaded when the last entity using it is despawned. So those are some of the common places you actually use resources. They're useful. The entities and components are going to be your bread and butter for actual game logic. In almost every case, for example, a player resource is almost always going to be wrong because then you can't extend it nicely and you can't work with it as cleanly in systems. Only one system can operate on it at once, and you can't share behavior. So creating resources. Unlike components, resources do not need their own trait implementation. You can use any new or existing static type, static Rust type as a resource. If it does not implement the send and sync traits, you'll need a non-send resource instead. Like entities and their component data, resources are stored in your app's world structure. Resources are typically added statically at compile time via app insert resources or app init resources. Insert resources is used when you want to set the value of a resource manually, while init resources is used when you want to automatically initialize the resource's values using the default or from world trait. Well, that formatting got messed up. So, here we are, and we're going to demonstrate how resources are, can be used. So resources, they can be tuple structs. You can derive defaults for many simple resources. The default value for most numeric types is 0. I suspect there is an exception to that, but I'm not sure what it might be offhand. Maybe rationals. Finally, next up, resources can be ordinary named structs. So here we have some player supplies. The default structs trait, you can again implement this manually to control initial values. Very useful. And you could have enums as resources. Again, useful trick. And typically, you're going to want to insert your resources using these app builder methods. Init resource uses the default value provided to implement it. And if for score, this is the derived default values from that trait. And here, for player supplies, it's using the manual impl of the default trait. And over here, we're inserting a resource rather than init resource, and that causes the causes us to have to set the value directly as a argument. Sorry, Radis, the execution order part isn't in here yet. So insert resource. So what you can do is you can use that struct override syntax with that default pattern to change some but not all of the values. Works really well when you're doing things like configuring existing resources from plugins. In this case, we're changing the window, and we're making sure that the title says that it is in fact a window. And then we're going to add these plugins, and we're going to call .run. So, in rare cases, you may need to add a resource later, once other parts of the world exist to ensure proper initialization. For that, we can use the equivalent methods on commands. You can add, overwrite, and even remove resources dynamically in that way. Only use commands to add resources where it's needed due to the need to initialize a resource with other data from the world. It's less clear, and like all commands that insert resources are delayed and only take effect at the end of the current stage. I've seen a lot of users of new beginners struggle with why isn't my startup system working and so on, because they found the commands to insert resources before they found the app builder methods to insert resources, and then they ran into horrible ordering timing issues. So commands are useful to insert resources, but they would be certainly not my first choice. Yay! So, Kart, is that are those changes are those changes live on my branch, and if I just pull, it'll work?
No, it's a new branch. You'd have to check out the new format dash fixes branch. Yeah, if it's too distracting, don't
Yeah,
let
that's
me sidetrack
probably
you. but
that's probably going to be too distracting for right now. Um,
yeah, no worries. No.
all right, so here we're going to talk about how we can read and write from resources. It's pretty straightforward. So here we actually have a game that you can play and is like kind of fun. You might make it in high school computer science class as one of your first projects. And this is just a guessing game to demonstrate how resources work. So here we have minimal plugins, we have a secret resource, and we have an input mode, enum. Then two systems to record the secret and check the secret. So as you can guess, our secret resource stores our secret key. Key code here that we have in here is for tracks which button was pressed on your keyboard physically, I believe, rather than logically. And it's useful to know that the default value of option T fields is always none. So when this is derived, it'll be initialized with no secret. Next up, we have some resource to control the interaction mode of our game. So this is an enum. Enums for enum resources to control simple game state are a nice pattern. If you need to get really fancy, you should do drinks. You should use proper states. Next up, we have our very first system here, which is storing the keyboard input in our secret resource. So here we have an input mode parameter, which grabs the mutable resource, and here we have a secret, which grabs it, and here we have an input resource. So basically what we're going to be doing is we're going to be grabbing so if the input mode is recording, we're going to print out a text prompt, and the very first time that it changed, and then we're going to grab the key code, and then if the key code was something, we're going to store it, and then and then here we have a line that is effectively just a bug fix to ensure that the other system doesn't spy on the data in the same frame. I am on the fence about what the correct choice is here in terms of teaching methods, because we could have this extra logic, or we could teach system ordering, or we could use system ordering without teaching it much here. My expectation upon review is that actually just using system ordering properly is the correct way here. Could somebody file a small comment on the PR to say, please just use system ordering in the guessing game comment? Because we've already introduced system ordering in the start of chapter example, so at that point there's nothing left to be done. So here we have check secret, which is again checking whether the input matches the stored secret. This is a cool example, probably a little bit long to go over in depth right here. So so if you check if the input mode is changed, then it gives you instructions, and then we are checking the secret and comparing it to the secret value, and then if that happens, then you go and change the resource back up. So resources alone can make cute little simple games, and this is a nice worked example for the extended period. So this is a useful little aside. So one of the things that came up both in our internal discussions and something that I see users asking a fair bit is, should I just use a single entity or should I use a resource? Because it's not immediately clear as a new user which ones make sense and when. So the pros and cons I'll jump into is the advantages of resources are you have a fast and simple access model. There's no need for queries. There's no need for unwrapping. You're not going to be accidentally broken. A resource of a certain type is always a resource of a certain type. If somebody ends up creating a second copy of that happens to match the components of your singleton, it's not going to work. It's not going to break things. And at the moment, we don't have non-send components in, and so if you need a non-send data within your to use that. So yeah, if you're trying to work with non-thread safe data, you must use resources because we don't have non-send components yet. Non-send components should be fairly straightforward. If somebody wants to tackle that, feel free. It'll be an easy-ish ECSPR. So Singleton entities, by contrast, tend to be useful because they can easily share behavior and data types with your other entities through systems that operate on their components. You can extend them, contract them at runtime by adding and removing components, and the change detection is much more granular. The change detection will be flagged as changed on a per component basis rather than on the entire object. And finally, allows you to only fetch the data you immediately need rather than the entire resource struct. In a lot of cases, this is over-optimizing. You don't care. But if you had a ton of assets attached, actually loading in a dozen assets rather than loading in the single asset that you need will make a noticeable impact on your performance because you'll get better cache locality by only loading in what you need. So overall, you should probably default to resources for one-off things. They're clear, ergonomic, work better. Singleton entities are great when you want to share behavior with other entities, or when you want to extend and modify the behavior dynamically. So if you have a player, if you have a camera, those should be singleton entities. But if you have something like the game score or what are all of my achievements, those might, or here's my audio library interface struct. Those are probably going to make more sense in resources. So, second last on this page, we have complex resource initialization from world state. Sometimes you may need to initialize resources in more complex ways, depending on the data from the world at large. From this, we can use the from world trait, which allows you to create a new copy of the type that is implemented automatically from the world. Ordinarily, the default trait is used to handle the resource initialization due to the blanket implementation of from world for t to default. Note that you can't manually implement the from world on a type that has the default trait, as Rust forbids conflicting implementations of the same trait. So the idea here is that, which could be clearer, is that you want to use from world when you want default-like behavior that depends on the other data within the world. Or if you need to use things like assets. I've seen from world used a lot to, say, initialize textures. And if you want more advice on how to work with the world exposed in from world, then we have a whole section on that, which we'll be getting to soon. Finally, we have optional resources, and you can wrap it in option. Sometimes a resource may not exist by the time a regularly scheduled system is called. We can handle both the case where it exists and the case where it doesn't by requesting option res t, or the appropriate underlying resource wrapper as a system parameter, and then branching on the resulting option returned. Here's a quick runnable example. So, this example dead easy. And what it does is it says we're going to have a countdown system, and we're going to count down by requesting a optional resource. And if so, this match statement is on the countdown resource, and so if the countdown resource does not already exist, we're going to insert a new resource with counting down to 10. If it does, then we're going to decrease this time by 1, and when we run out of time, of course it says kaboom, and the app exits. So that's how that's how that works, and that should be minimal plugins if somebody wants to make a note. I lied. There was another section that I had forgotten about. So resources that are not thread safe. So non-send resources can be used to store data that does not meet the send plus sync trait bounds. They cannot be sent safely across threads. Their use cases tend to be typically quite advanced and tend to involve interfacing with external libraries for things like audio and networking. I haven't seen a lot of examples of where you might want non-send resources outside of external library interfaces and async task management, I think. Perhaps. I'm sure Meatball knows better. But when you want them, you definitely want them, and otherwise you can ignore they exist. So the way that non-send resources work is that the system that if there is one or more non-send resources in your system, that system will always run on the main thread rather than being automatically scheduled to the first available thread. This ensures that the data is always accessed from the same thread, no matter what combination of not thread-safe objects you may need to access. Next up, we have systems. So systems do work. So this is where we can actually get into the details of systems, which are the fun and interesting parts. In order to make useful, fun, or interesting games or apps, you'll need to manipulate the data that you store in components and resources in some way. In Bevy, virtually all of your logic will be stored in systems, functions that automatically receive data from the world from the scheduler according to their system parameters, and can mutate data to change the world. Any types which implement the system param trait can be used as a function parameter in your systems. This trait tells the scheduler how to pass out access to the world in a safe and efficient way. So most commonly, you'll be using query to access the entity component database, res and resmute to access the global singleton data, commands to queue up complex changes to the world, and event reader and event writer to work with events in an ergonomic fashion. Those will probably cover 90-95% of all of your system parameter needs, and they work quite well. You can see there's more of them though, and you can see the full list of system parameters that are included inside out of the box, not outside of the box, by checking the API docs for system param. And if you would like, you can even add your own custom system parameters that you can stick in your system by deriving the system param trait on structs where the fields are all impulse system param. Okay, so we're gonna take a digression since I have an audience here and some folks talk about Supermath's points. So Supermath says, I feel that more advanced parts of each chapter should be put in an advanced book. Then there should be a beginner book with everything else. So this is something that we've gone back and forth on. It's nice to have the signposting, and it's nice to have the clear logic flow, but it's also nice to be able to look something up and know, okay, I'm going to check this the section on components, and then I'll have all of the information for components. And how do we want to balance those competing needs that we have? And there's a section in here called Understanding the Magic that is particularly bad for that. But even things like exclusive world access and some of these digressions on custom system parameters and so on that really don't really don't belong in a beginner's introduction. Gladys's point is useful there. There's a difference between mentioning something and going into detail. That's something that we could probably do better. So things like non-send resources would be good. I would also be really tempted by an advanced marker within here. I think might within each page. I think is probably going to be the better approach to do so. Kurt, do you have opinions on this? I know we discussed this in the initial RFC and we went back and forth, but now that we have more of an example,
Yeah. So I do think that it's worth kind of playing around with different permutations of these things, and most of this content wouldn't need to be rewritten if we say extracted all of the advanced stuff and put it into its own section.
yeah, put it into an own section, or even just give an advanced note in the section in whichever section titles. So, like, say, generic systems here would be advanced generic systems, which may be
Yeah, exactly.
maybe more common.
And yeah, I think that so we had a pretty long back and forth on the structure and like what makes sense and
yeah, no,
we kind of
and
bet
I
on
wasn't
this
fully
one,
convinced either.
but
So
I don't. Yeah, I don't have strong opinions yet. I think that it's right to call out that there is some stuff that is advanced that breaks the flow, and I think that we should just try a bunch of different stuff and see what sticks.
yeah, and I think we should also try to ensure that all of the advanced sections try to belong at the bottom of each page when possible. So there,
Yeah.
and then clearly demarcated. We could have a shortcode for advanced, which would be kind of interesting. Do we have search functionality on the book yet, Cart? Or no?
We do not.
Okay.
It's something that might take some investment on the Zola side.
Yep, that makes sense.
I know they have like a built-in search thing there. It's pretty limited in my experience, both in terms of like how it queries stuff and how it's like displayed to the user.
Yep.
But yeah, I think we can make that work.
Okay, because
without too much work.
We may at some point want a short code for advanced, and then have a way to like search for all of the advanced stuff. Might be fun. Okay, and I think that
totally
in
true.
general, having search functionality within this is going to be very useful if we're using this as reference. Although, and that's part of why the lack of built-in search functionality is why I'm really reluctant to like split it out into an advanced book and a beginner book, or a or like a ECS advanced page, because like who knows whether what's going to be on that ECS advanced page, and without a search functionality, you're never going to discover it.
Yeah, agreed.
Yep. All right, sounds good. And so let's get back to it. So as systems are added to your app using add system or one of its sibling methods, which will cause the added system to run once on every pass through the game loop. So here I decided to deliberately not talk about stages and scheduling and so on, because that to me belongs in the start of the next chapter, game logic system ordering. I think that it's clearer to focus on the data models in this chapter, and then all of the how do we actually turn that into a useful working application logic flow in the next chapter. However, startup systems are worth calling out here because startup systems are used constantly and described constantly. So in many cases, you don't want your system to run constantly. Instead, you only want to have them run a single time at the beginning to perform some setup. To do this, use a startup system. Startup systems will run exactly once before any ordinary systems. Ordinary being kind of fuzzy term for systems registered just with add system, and you can add them using the add startup system method on app. Carefully controlling if and when systems run is one of the most important tools you have for managing the behavior of the game. Check out the pages on system ordering, run criteria, and states in the next chapter for more details. So this is advanced generic systems. So this is a cool trick that Avery actually really introduced me to the uses of. you are not limited to just one of a single system. You can insert more copies in different places throughout your schedule when you want to perform the same work repeatedly. This becomes particularly useful when you combine it with generic types. Creating generic systems whose behavior is specialized on individual types that you pass in when you add it to your app. So generic systems are useful for repeating the same logic across many related types and are incredibly valuable for library authors who wish to provide configurable APIs that mesh nicely with the user's code. In the latter case, note that entire plugins can be made generic like this. All of the standard tricks for Rust generics work when used in systems, allowing you to create systems with trait bounds, multiple generic type parameters, and even const generics. I do have a I do have a link to the later chapters here. That's what these links are. Perhaps there should be different formatting on that, maybe perhaps something more standardized or short codes even. But at the moment we do have links. With respect to the startup systems meatball, I would love to get into that with you later in the ECS dev. Next up, we have commands. So commands queue up work. Commands are powerful, unrestricted tools for modifying the world of your Bevy game. Queue them up, and you can reshape the world in arbitrary ways when they're evaluated. Commands are fundamentally designed to perform work that cannot safely be done in parallel, and are used to change the world in ways that touch large amounts of data at once, requiring exclusive access to the archetypes and other metadata of the world. While you can check out the full list of options by reading the API docs for commands and entity commands, the commands that are most commonly used are spawn and despawn entities with spawn bundle, and despawn. Add and remove entities, resources dynamically with init resource, insert resource, and remove resource. Add and remove components to entities with commands insert and commands remove. Due to the limitations on parallel execution of the operation performed using commands do not take effect immediately. This is, by and large, their defining characteristic. They must wait until the next hard sync point, where a single function has access to the entire world in a sequential fashion, in order to be resolved, as they require exclusive mutable access to the world. Unless you are already operating in an exclusive way on the world, commands are typically going to be processed at the end of the current stage. As a result, avoid using commands unnecessarily. For example, you could use the overriding behavior of component insertion to mutate components in place. However, this is unclear, slow, and takes delayed effect, making it strictly worse than just requesting the appropriate data and mutating it in an ordinary fashion. Don't do it. It's please try not to deliberately overwrite existing resource or component data using command insertion. Yeah, commands are bad, kids. Don't do commands. But there are some things that you will have no escape from at the moment. Entities, entity and component operations are the most common, but mostly you can get away without them. So using commands. So as discussed in this earlier chapter page called Entities Have Components, commands are used by adding a commands type argument to your function, then calling various methods on it. For basic overview, please refer to that page. For more details on the available methods, check the API docs. Probably repetitive. Finally, so this one is advanced, custom commands. So you can extend the command trait to create your own custom commands, performing tasks with far-reaching consequences without requiring access to the data in your originating systems. Let's walk through the steps needed to create a custom command. So this is a very useful reference. I couldn't find anything that described how to use this, and I've had to look this up a couple of times. So first, you create a struct that stores any data that's needed by the command. So in this case, we're creating a command to count entities. It has some data called string. Called the message, which contains a string. It doesn't do anything useful, but next you implement the command trait for that struct, which describes how the command changes the world. So in this case, we're implementing the command trait, which has one required method called write, and we are using an info. This world has has so and so many entities in it. By the way, here's your message. And then we're using string interpolation to add the number of entities in the world, so the world's entities method, and then the length of the iterator returned there, and the message that's actually stored in our commands. So then what you do is you add an extension trait, which allows us to add new methods to commands, capital C commands. And in this case, we're adding the count entities method to it. Finally, we implement that trait for the commands type, adding our new command type to the command queue. So now, once we have this final trait implemented, we can call commands.countEntities message, and then it will add this command to our list of commands, and then that'll get pulled in, pulled in, and then when the command, and then when the commands are being executed, the command trait will be the write method will be called on each of those objects within that vector, which will then cause this logic to execute. So that's those are kind of the loops that you need to jump through in order to create custom commands, but those can be quite useful.
So one quick call out here. All the extension trait stuff is completely optional. You can also just call commands.add
Right.
on like the actual type.
Yep.
So you could say like commands.add count entities and then define the message inside of the struct. And I think for a lot of cases, it's probably better to just do that.
Right. Yeah, that's fair.
But if you're building like a library or something, like you might
Yeah,
want to do the extension
and
trait stuff.
To me, okay, right, yeah, that's worth calling out. I'm gonna make a note here. Extension trait. Yeah, so I think it's worth presenting both of them, but explaining that you don't need to do it. I'm more used to working with commands as a engine author and as a library author who's really trying to optimize for ergonomics and so on. So I'm used to the extension trait. But that's absolutely correct that you don't need to do it. You could just use commands.add. So again, commands have a lot of caveat. Don't use custom commands unless you really need to. In most cases, you can just use an event handling system, and it will be faster, more ergonomic, and easier to debug. Again, it's the general principle that you see in programming, where you should try to make your API and as narrow as possible, and have as limited of possible splash damage. Nice modular, clean interfaces, and commands are something of the opposite of that, which sometimes you need, but if you don't need it, use a smaller gun. Yep. Commands performance is also not very good compared to a lot of the other stuff, because it's not vectorized, it's not run in parallel. There's no smartness. It's like you're writing imperative code, and so if you have 100,000 of them that are running every single frame, you're maybe not going to be the happiest. Especially if they're custom commands that we're not going to be able to optimize for you. So next up, another advanced topic. There's a really nice little trick you can do to manually flush commands. This is particularly useful if you're writing testing code. If you're using Bevy ECS on its own, you're probably not using commands at all. But for this, if you're writing testing code, so if you have exclusive access to the world, you can use system state commands apply to immediately run and clear any commands that you may have accumulated. This was new to me, and it's wonderful. It's very, very useful. You're not going to run into this. So generally speaking, this isn't useful for the average game. You can't get exclusive world access any faster than commands naturally apply. However, this technique can be incredibly useful for advanced control flows. So if you're writing systems, running them one at a time, and then wanting to flush them, if you're willing to sacrifice in parallelism to immediately or repeatedly process commands, this can be useful. It can also be useful for writing tests. So I've run into users who want that sort of thing first. So here is a little bit of a digression, another advanced digression about the mechanisms of commands. So, due to their special nature, the internal mechanisms of commands are not entirely clear upon inspection. This section discusses a few of the details that can matter as an advanced end user. System parallelism and commands. Interestingly, more than one system can add commands at once. This is safe to do so due to the append-only nature of the data structure. Because usually, we're writing for something in two places at once. You can't do that. Instead, the way that it works, as I understand it, the code was not the easiest to follow. A fresh command struct is dispatched to each system, and then each instance is processed later according to the execution order of the originating systems. So basically, we're using a fan out and then weave together at the end strategy. This is quite useful because it increases system parallelism in important ways. A lot of systems use commands, but this is very different than the standard logic applied by other Bevy resources, including events, which use the standard no alias mutability logic. Next up, application order. Application of order of commands can really bite you if you're not paying attention to it. So when you're combining the effects of multiple commands, it can be important to know their order. If one system is spawning an entity and then another one is passing off its entity identifier to another system, that needs to occur before the second system attempts to add components to it, because otherwise you'll get a strange error message and maybe a panic. Thankfully, while the effect of commands is delayed, the execution order follows a few simple rules. So the first one is commands are always applied one at a time. Second rule is all commands created by a given system are applied sequentially in the order in which the methods were called on the commands object in that system. If you have internal parallelism, that's magically waiting to commands, but you can't even do that. So yeah, no, it'll just be in the order that it's applied. If systems ordering is explicitly specified, that ordering will be respected. And if you don't have an explicit order between two systems, if the order is ambiguous, including transitive ordering, then the order in which the commands apply is unspecified. It's basically our own version of UB, and it may vary between runs of the app. In a lot of cases, this won't matter, but if you are getting okay, it's not UB. Okay, it's not UB because UB is only memory, but it is behavior which is not defined, which is definitely not UB. And it is non-deterministic behavior, and that sort of thing will tend to manifest in bugs that appear only on some runs of your game, but not others. And if that is occurring, you probably have an important system ordering that you're missing. All right, 4 more to go. So this one is fairly quick. So this is responding to changes. This is all about change detection. Bevy allows you to respond to the addition of or changes to specific components type using the added and changed query filters. These are incredibly useful, allowing you to automatically complete initialization of components, keep data in sync, save work by only operating on entities where relevant data has been updated, and automatically respond to changes in the data of UI elements. So these change detection features are really powerful, and IMO are one of the distinguishing features of Bevy at the moment. So a component is marked added on a per system basis if it's been added to the entity via component insertion or being spawned on an entity since the last time that system ran. Similarly, if a component will be marked as changed on a per system basis if it has been added or mutably dereferenced to the last time that system ran. As you almost always need to mutably dereference data out of its wrapper in order to mutate it, this will give an accurate and fast indication that data may have changed. Change detection works for resources too, using the exact same internal mechanisms. Use the isChanged and isAdded methods on any resource or individual entities to check if they've been added or changed since the last time that system ran. So added and changed are both query filters, appearing in the second type parameter of our query data types. Let's look at a little snippet of gameplay code to see how it works. So you might use an addition tracking system to automatically change the difficulty of your game's enemies. So this is a neat little example. So we have an enum difficulty, which is going to be a resource, and difficulty. Each difficulty is associated with a modifier, which scales the life of our enemies. All right, um, and then we match on it, and we get the modifier out. Nice and straightforward. Next up, we have our life component for our entities, and here we have an adding an addition detecting system. So as you can see, the syntax looks just like query filters. In the second type parameter spot, you have added life as your type parameter. So this says this system basically detects all entities that are spawned with a life component or had that entity component added, and it will go and modify their life accordingly. And because of the way that the change detection works, each relevant entity will be affected exactly once by the system, no matter when the other system ran or how long it's been between the systems running or so on. It works the way you would hope it to, not the way that you might expect it to, which is lovely. The reason that we can't, so from kind of an architectural argument here, you don't want to just change the values that our entities spawn with, because that modifier can change at runtime, and like if we're adjusting the difficulty of a game, you want to be able to do this in a more programmatic way, rather than going and altering the underlying data. So next up, we are looking at some change detection of resources to extend the difficulty changing example. So if difficulty changes in the middle of our game, existing entities won't be modified correctly. Let's fix that with a demonstration of resource change detection. So here's an example. It has some nice little logic in it, and the core bit to extract here, as we're reading along relatively quickly, is the difficulty.is changed. So here we're tracking what the old difficulty was in order to make sure we can properly adjust for it. And then over here in the difficulty change systems, we reverse the old difficulty modifier and then apply the new one. So here we have change detection, and we have change detection, and we have a change transform. We're demonstrating how we might use change detection to save some work while detecting whether enemies have escaped. Because it will only be looping over and performing this expensive range finding operation on entities that have moved. So this is another advanced section on how does it actually work. So change detection in Bevy uses a custom implementation of the deref mute trait on mute and res mute, which are mutable wrappers for components and resources. If you're a Rust expert, you'll notice that this has some interesting implications. So basically, deref mute is a tool to unpack a reference to get access to it mutably, but you don't need to use deref mute to cause to mutate internal values when you're using a pattern called interior mutability. You almost certainly want to manually flag the data as having changed using setChanged when you use interior mutability. You can just bake that into your getter methods, into your setter methods rather, and that will work nicely to make sure change detection stays accurate. It's a nice thing to do to other users of your APIs. The other thing to note is that changes will be flagged whenever you mutably dereference to access a component or resource, even if you don't change its value. Don't mutably dereference things unless you are actually going to change the values. So try to make sure that you're checking, do I need to change this before you actually unwrap it, and that'll avoid false positives. Next up, we have a tool called removal detection, which watches for the removal of components. The mechanisms are quite different. It's not a query filter. It's just another system parameter, and what it returns is an iterator of all entity identifiers, capital E entity, with the components of that type, and if the components of that type were removed from that entity last frame. This also includes entities with that component who are despawned, which is really important. This is effectively for cleanup purposes. There are some important caveats. This only works for removal detection. Only works in the last frame. It's removal detection plus fixed time steps is going to break horribly. Removal detection plus states is probably going to work. The next caveat is that, wow, that formatting is super broken, is that removed components don't return the value of the component that was removed. And so if you need the value, you have to write your own change detection system to cache the values. And then the next one is that remove components is a system parameter, not a query filter. If you want to, filter a query by it, you're going to want to do some manual comparison. So, despite these caveats, removal detection can be quite useful for cleanup and toggling behavior through the addition and removal of components. So, oh my god, that's super broken. Okay, Kart, your branch is it's time to use your branch.
Yay!
All right, let me check that out. Oh, come on. One moment. There we are. So I'm currently checking out the branch, and then I'm gonna go Zola serve. And with the magic of Zola, I should just be able to refresh my page, and it should work. Aha! The formatting is fixed. Perfect. Okay, that is much more legible. So, now we are on to a whole page that is just advanced. So, this is about exclusive world access. In various places, Bevy code works directly with the world data, gaining exclusive blocking access to it and allowing for arbitrary mutations. This is very flexible and can be essential for advanced use cases, but prevents any other system from running simultaneously and can often be harder to reason about and maintain. As a result, you should only use exclusive world access when you have to. You might be working with the world if you're running an exclusive system to access data in unusually broad ways, such as for saving the game or handling networking. You're writing a custom command to execute logic at the end of the stage. You're initializing a resource using the from world trait. You're working with non-send values that cannot be sent across. No, that's wrong. That's just wrong. Can somebody please leave a note complaining to me about that? And you're setting up tests to be run in a headless fashion, or you're using Bevy ECS as a standalone crate. Generally speaking, the API of working directly with the world mirrors those that you might be familiar with elsewhere. So, like with commands, you can call world spawn, despawn batch, despawn to add and remove entities. You can add components to them. You get resources, and you can also get the component data of particular entities using world get. If you want to access all of the data on a particular entity, get entity is correct. along with along with the various methods on a struct called entity ref on that object. I call that out there because it's often quite difficult to discover. You can create new queries using world query and world query filter. Use the former when you only have one type parameter, and the latter when you want to use the second filtering type parameter of standard queries as well. I believe world query might be slightly faster, and that's why we have two separate APIs, but I didn't write that code. Exclusive systems. So exclusive systems can operate on any data at once. No pesky, carefully scoped data access needed. This comes at a great cost. No other work can be done at the same time. So if you want to pretend that Bevy's parallelism doesn't exist, and you just want to write straightforward imperative code that can access whatever it wants, that's how exclusive systems work. I've seen people using it for turn-based games with reasonable success. I'm not sure it's my favorite approach, but it certainly works for them. In order to make an exclusive system, ref world must be the type of the only parameter in that system. All of the other data that you might want to add as a system parameter can be accessed using the world's methods on the world. If you let the schedule know that systems are exclusive using .exclusive system on that system function, and then you just add system like usual. Unlike ordinary systems, which can be executed in parallel in arbitrary orders, exclusive systems can run either immediately at the beginning of immediately before the start of a stage using @start. Immediately after the end of the stage, but before commands are applied, using before commands, or immediately after the end of this, after the end of a stage, after commands are applied, using @end. Those are the three. Those are kind of the three buckets that exclusive systems fit into under the current scheduler API. See if we are getting into it. So @start is the default behavior of exclusive systems and can be omitted. Like other systems, exclusive systems obey standard ordering constraints, as discussed in the next chapter, which isn't written yet, but only with respect to other exclusive systems running at the same time in the same stage. Trying to say that this exclusive system runs before this before this ordinary system, it doesn't make sense. Just put it in a different stage or in a different part of the stage accordingly. So here we have an example of where we might want to use the far-reaching power of exclusive systems. So this is from Jasmine. This is from her turn-based example. And here we have a custom action stack to queue up freeform actions to enable complex, flexible logic. So we have a trait that allows us to store complex, arbitrary, world-altering logic. It is a trait action with a perform method, which mutates the world. So this is kind of like our own variant of commands. It is very similar in terms of conception, but it'll operate logically. It'll operate immediately. So here we have a stack of actions that are executed in first in, last out order, and then our perform next action exclusive system takes the top action from the stack and runs it, repeating until the action queue is empty. So as before, it takes world to ref world as its argument, and then it just loops. And it says we grab the action stack resource and unwrap it, and then we pop off the first item, and then if there's an item there, we perform that item on the world, and then we call break. We break out of the loop once there is no actions left. And so what this allows you to do is it allows you to work with a very different style of game architecture, where rather than carefully running things each frame, we're processing these actions one at a time in a way that may make more sense for turn-based games than the standard perform logic every frame that makes sense for like arcade games and shooters and so on. So here we have some extra advanced bits of the world exclusive world API. You When you're writing non-trivial exclusive world logic, you may need to access multiple parts of the world at once and immutably. And what oh huh. Um, so there are two main ways to do it, where basically you're partitioning the data access. So the first one is world cell. Um, so this enables interior mutability by disabling Rust compile time checks for alias mutability and replacing them with runtime checks. If somebody has a better explanation of that, I would love it, because I didn't really quite understand what was happening. Foskers? No, okay.
Hello.
Oh, did you? I thought you were going to say something. So the other approach that you can use is you can use a resource scope, which basically temporarily removes the requested resource from the world and then returns it at the end of the function or whenever the created scope is manually dropped. This is super useful. I think that the example above actually needs a resource. May actually need a resource scope to work safely, but it allows you to have multiple mutable references active at once. So the next trick that's super useful is accessing system parameters. So this is the nice new system state API, and what you can do is you can basically extract out the state of a system from the world, and then as if it was a normal system with these parameters, and then you can unpack it into a tuple, and then actually work with it. So this is kind of a hybrid approach between exclusive world access and the nice friendly API, friendly and scoped API of systems. Next trick that you can do is you can manually run systems. This is super useful for testing in particular. The trick is that you just need to so we have our system, and then we call system dot system hello system dot system dot initialize on the world, and this passes in the world to make sure the system is set up properly, and then we run the system with hello system dot system dot run world, and then we can immediately apply any buffers like commands that are created by the system to the world by using the dot apply buffers commands. This is not going to be very performant, but it can be flexible and simple. This is very useful for testing in particular. And also for code organization within exclusive world access. So this section, I'm not quite sure where it belongs. If anyone can have suggestions on where this might fit, I'd be happy to hear them. So if you're new to Rust, so this section is basically, there's a couple of tips and tricks and weird Rust things that are going to trip you up when you're using Bevy and when you're using the ECS. I'm not sure where this, I think this is the wrong spot, but I'm not sure where it should go, so I'm happy to hear suggestions, but I'll get it out. So, Rust tips and tricks. If you're new to Rust, there are a few standard patterns and pitfalls that are particularly relevant to Bevy's ECS. Feel free to refer back to this section later as you learn more about Bevy. Maybe at the end of the welcome chapter. Tuple structs. So tuple structs, defined like struct score bracket U64 bracket or position U8 U8, are structs with unnamed fields, accessed by the order in which they were defined. .0, .1, and .so on are used to access fields, counting up from 0 in the order that they were declared. My position .0 equals 42 can seem opaque when you first read it, but in Rust it means that you're assigning 42 to the first field of the tuple struct my position, and by convention that's the x-coordinate. Using ordinary structs with named fields rather than tuple structs, even for simple components and resources, can go a long way to improving the clarity of your code by providing more descriptive field names. In this example, my position.x equals 42 immediately communicates intent rather than relying on the end user to remember the convention used. So, smart pointers. There are a few points to be aware of when working with smart pointers, like we use for our components and resources. So, the value returned in a system when you ask for res score is not a plain score. It is a res score, which is a resource that contains a score. And it works similarly to an ordinary ampersand reference, but with some special behavior on it, like change detection. Because res and other smart pointers implement the deref trait, Rust will automatically attempt to dereference it to match the required types when it can. This commonly happens when you're grabbing the fields and methods, so this is why calling .title on a res window descriptor grabs the actual title field of the window descriptor. It'll continue to penetrate down the stack until it finds the first matching title, but it's this can be a little bit implicit and magic for how that fits. So this is a good digression from my man, and is how important is it to discuss fundamentals of Rust in this book? Describing how tuple of the field access works is out of scope for the Bevy book. So this is intended, in my view, to help beginners with common Rust things that confuse the heck out of them, and they're not going and things that they're not going to immediately stumble across when they're reading the Rust book. Things like smart pointers, things like what the heck is .0, things like how does struct initialization work, struct update syntax work. Those things are not something that you're going to encounter if you're just doing Rust things. If you're or if you're reading through the Rust book for the first time. And I've commonly seen beginners, including myself, who encountered this and looked at Bevy and were completely baffled by the standard. Yeah, .0 is the only one that .0 and the tuple struct stuff is the only one that I think should really strongly be considered cutting. For the recording, I'm currently reading the text over in general text, and I'm trying to wait for others to have a chance to talk. So yeah, the other things that we cover here are default structs, struct update syntax in particular with defaults. And the last one is that type aliases don't work. Type aliases do not play nice with the ECS because they'll have the same type ID. Yeah, so Meatball, I think that you may be right. Try and cover to see if we can move some of this other stuff. I think that the tuple stuff has been covered adequately in comments elsewhere, which has been great. And I think that The type aliases don't play nice. I'm not sure where that belongs. If we had a gotchas page or like common debugging, like the cheat book has, I think it would belong there. But without that, I'm not sure where it would belong. And I think that the struct update syntax can actually also be cut with because it's already covered under the bundles page. So yeah, maybe we dissolve this entire page and stick like smart pointers in under like the resources page or something, and then type aliases we can like, I don't know, punt to the cheat book, make an issue for it, or make a gotchas page. And maybe the smart pointers and type aliases belong on the gotchas page. Yeah, smart pointers. So I don't know that smart pointers actually belong in the next chapter because they are fundamentally something that you run into when working with the ECS, and they're not about how we organize the logic and like the game flow. I think that they may. I think that should probably be worked into the resources, and we should perhaps have a explicit beginner tag for talking about dereferencing smart pointers like resources. Because resources are really the place where you encounter them the most, and if it's explicitly signposted as this is for beginners, it should work pretty well. Not the next major chapter. The next subsection, the understanding the magic page. Yeah, that could actually work fairly well for. That might actually. Yeah. Although no, yeah. We can chat about it in the PR, but I'm gonna try sticking them into the resources page and see if I can dissolve everything else. So here's the fun bit. I'm gonna link this to. I'm gonna chat about this to general because this is actually useful. Actually, no, whatever. So here's the fun part. This is the really interesting thing that I spent a while working on yesterday, and this is very clearly advanced. This is targeted at people who see Bevy and say, how the heck does it work? And aren't willing to just let it go and just accept the magic. They insist that they must have a basic understanding of how does this work before they feel comfortable with it and before they're ready to start experimenting. And it's also very useful for people who are actually interested in jumping into the engine code for whatever reason, whether it's their own hack or contributing. So, understanding the magic. At this point, it's common for new Bevy users to have a few questions about how the high-level tools you've been introduced to actually perform their feats of cunning ergonomics. You may have wondered, how does Bevy convert a function to a system when we call app.addSystem? How does the app know which data a system needs access to? How are systems called by the main game loop? How does each system actually get its data? Because when you see a system, when you see Bevy and you see the examples, you're like, that's exciting. It's how does this work? How is this possible? And the answer is a lot of complexity under the hood. So how do we add functions to systems? So conceptually, this is pretty straightforward. We pass in our functions as first-class objects, we examine their properties, we store them in the schedule, and then we call them repeatedly when our apps want to request them. But that's kind of a hand-waving explanation. How does it really work? So we can pick up the trail by examining the add system method. We find that it's generic over any type that implements the into system descriptor trait. So this trait defines a conversion between the underlying function and the system descriptor representation, which stores scheduler relevant information, so like whether it runs before or after, and as well as the system itself in boxed system form, which is just a boxed system trait object. Once a system is neatly boxed up, we can examine the methods of the system trait, which provides an interface to access all of the interesting information about the function that we've transformed into a system. The most important method here is system run, which allows the callers, like a schedule, to correctly run the system. Functions are converted into systems using a blanket implementation of the into system trait, allowing us to extend existing functions whose signature meets our criteria. By calling the into system method when we attempt to run our systems, our function starts its path to becoming a well-behaved, fully initialized system. So, this blanket implementation in question covers the impl in out param marker f into system in out is function system param marker for f, where f implements into system signature, of course, which is relatively nice. And here, at the bottom of our stack of abstractions, we find the heart of the magic, a collection of implementations generated by macro due to the lack of variadic generics that describe how to convert functions with arguments that implement system param, along with an unsafe run method. And that's where all of the really, really interesting bits of code live. So, how do systems know which data they need access to in order to enable multiple systems to safely and automatically run in parallel? We know that we have these functions that we're passing in, and something to do with their types, and then this type information is somehow dynamically converted at runtime. But we know that how does it actually do that? So in the system trait, we have two relevant methods: component access and archetype component access. The access struct returned by those methods keeps track of the read and write accesses of a system, either on a component ID or archetype component ID. These store the types of each resource and component as a cheap, safe identifier, ultimately created out of a type ID during type registration, which automatically occurs the first time a component or resource type is used. This fundamentally is why we're limited to one of each type of component per entity. We use this type information to dispatch data. Through the use of access is compatible, we can determine if two systems have compatible data access patterns and block them from running in parallel if they do not. This can be done in a smart cached fashion and is combined with explicit system ordering constraints to create a list of systems and their constraints. Systems are run in a greedy fashion, scheduling the next available unconstrained system as soon as a thread is free to accept work. I am getting into the scheduling stuff. But of course, every answer leads to more questions. How does Bevy know which access a system will need based on the arguments of the underlying functions? To get to the answer to this question, we must turn to the system param trait once more. You'll recall that every parameter in a system must implement system param, and this information is somehow transformed into the fully fledged system implementing object, which has the access information we're curious about. The key is in the associated type fetch on system param. This type must implement the system param fetch type trait, and stores the information we need inside a system meta field. Inside that is a private field, archetype component access, which stores an access archetype component ID, allowing the implementer to define the component data at an archetype level of granularity that are accessed by the system parameter. The accesses of a system are defined as the union of the accesses of all its system parameters, allowing us to convert it from the access needed from each parameter into the final form needed by the scheduler, concluding our detective work for the day. So, the next question is, what happens when we call app run? Well, on the surface, it's pretty simple. Our runner field of app run stores a function in the form of a box-dine the runner, which is a boxed function that takes app as its argument, is called. And by default, this begins as a box new, run once. which is a trivial function that calls app.update a single time. When this method is run, the world schedule is initialized, running it as a stage. Stage run takes immutable reference to the world, and its implementer contains all of Bevy's scheduler and dispatch logic, allowing us to carefully dole out access to our data in a safely parallelized fashion. Yes, I agree. Radis is a great quote there. To our collective benefit, the scheduling algorithm itself is dead simple. It's getting to it. That's the unadulterated sorcery. The simple update the app once runner logic can be easily customized and changed, both by the end user and by our default plugins, whose Winit plugin changes the runner to Winit runner, which repeatedly updates the app and interfaces with Winit to establish windowing and input handling before the system scheduler is run. The last question here is data dispatch. There's one last piece of the puzzle. How do we actually pass references to that data from the world's archetypes, from the world into our I think that's wrong. From the world into our system when the schedule is run. I agree, Meatball. We need the test tube emoji here somewhere. For parallel systems, the logic is contained within function system run unsafe, which is called by their implementation of system run unsafe. Ultimately, the data is fetched using the unsafe method system param fetch get param, which extracts the information specified in system meta from the world directly. The safety of this is fundamentally upheld by our executor, which runs our schedule according to a particular strategy. Executors must update the list of archetypes that exist in the world each frame to ensure that the system data access is safe and avoids false positives by splitting a column-like component data storage into non-overlapping sets based on the collection of components that entities in the world actually have. So basically, we're partitioning the data in a way that's more granular than just the columns, because we know that some of these columns are never going to intersect in the ways that matter, by virtue of which rows and columns are actually filled. It's very Sudoku-like, but this allows us to get even better system parallelization in very important ways. So the default executor used in Bevy is Parallel Executor, which executes systems in parallel in a simple and non-deterministic first-come, first-served fashion that respects system orderings. Check out the source code and the section on system ordering for more details on how this is done. All right, so that's the end of the chapter. Thank you guys for your patience. That was a lot of time, and it was fun, and we caught a lot of issues. Hopefully, I remember them all when I go back through to make all these edits. But thank you guys so much for listening, and that's the start of the new book. Hopefully, it leads to some excellent improvements for new users and new and old users. A lot of this is actually quite advanced and useful for other stuff. I have a recording going too, so like in the worst case, I can seek through it and spend 3 hours to slowly go over this.
That'll be fun.
Yeah.
Thanks for doing this, Alice.
Yeah,
this was really great.
That was totally worth it. Good for teaching and getting community engagement, but also really good for some discussion on what does the new book look like, what can be changed, what works, what doesn't. And I am really excited to have the whole book written. Like, it's if we can get something like this for everything, that would be so incredible.
Agreed. Totally agreed.
Yeah. We should really get the examples compiling though, so we don't run into stupid, embarrassing issues that break when users try and copy paste them in.
Yeah, that's pretty important.
Yeah. Also, maybe some deadlink, some checking for like malformed shortcodes, I guess.
Yeah, that would help too. Definitely would help.
Malformed shortcodes and changing the shortcodes to not include the whole module name by default, because I have a couple places where I'm like, I definitely didn't want the whole module name in there, but it's in there.
Yeah. Yeah, the dead link checking has been really bad for CI recently.
Yeah,
like, we get so many failures even with our retry logic.
Yeah, no, and I'm reluctant to add more, but like it's so important. It's so bad as a new user when you click a link and it's dead, and you're like, oh god, what is this even supposed to go to? And like,
Yeah.
yeah.
Totally agreed. Yeah, I'm not advocating that we should remove it. It's
But
definitely kind of critical.
yeah, it's rough. Especially if we want to get the methods working properly. But yeah, thank you guys so much. That was fun.
Yeah.
I think that separating out the advanced stuff, signposting the advanced stuff more clearly should help the flow a lot. Does anybody have any
Yep,
other questions?
agreed.
Questions, comments, concerns?
I'll have lots of comments once I start.
Oh,
my,
absolutely.
My review of the ECS section.
This was fun. And thank you, Kite, in particular, for showing up, because this will make the review process easier for you going forward.
Yeah, totally agreed. Yeah, thanks for doing this.
Yeah, no, it was a fun way to spend a Saturday evening. So hopefully it has helped some of the beginners get some more confidence too. All right, I'm gonna wrap up recording now. I'm happy to continue chatting in general text, but I think that's good. Thank you guys all for coming.